This video is going to go over the Pythagorean Theorem in brief. So, when we think of the Pythagorean Theorem before a geometry class, so like a trig class or a calculus class or some other class that's using Pythagorean Theorem, you typically think of some triangle. You gotta have a right triangle. You think of the length of the side of the hypotenuse is C. You think of the length of the two legs are A and B. And the Pythagorean Theorem says if you square A and square B, add them together, you'll get the square of C. And A, B, and C here are all the lengths of those line segments. Okay, but that's not how Euclid puts together the Pythagorean Theorem. We're thinking now in geometry and we're not using algebraic formulas. This is going to be done differently. Okay, so I've got pictures that are going to fly in here, but let us talk about the actual statement first. The actual statement of the Pythagorean Theorem in Euclid's first book, it's near the end of the first book, where he talks about area of a lot of different things. It stated, prove that the sum of the areas of the squares on the legs of a right triangle equal the area of the square on its hypotenuse. Okay, so I've gone ahead and prepped up a little right triangle for us. The right angle is up here at angle A. So it's flipped from how you normally see it. And what I'm going to do is I'm going to go ahead and put some squares on this. Okay. So when it talks about the sum of the areas of the squares, he's talking about these three squares right here. Each square is on each of the sides of the triangle. And when you say a square is on the side of a triangle, it means that one of the sides of your square corresponds to one of the sides of your triangle. Now, what is this telling us? This says if we calculated the area on this little leg plus the area on this little bit longer leg, and it's fine if they're actually congruent, then when you add those two areas together, it's a number, so you can sum it just fine. You're actually going to get the area of this guy right down here, this square on the hypotenuse. Okay, now let's see how this would actually work. So now I'm going to very, very hand wavy in brief outline what you would do to prove this. Okay, so in terms of the outline of the proof, and this is the main thing of the proof, is we're actually going to be dealing with all of this stuff in terms of figures. So instead of bumping everything immediately to numbers, and when I say numbers, I mean immediately to area, what we're actually going to be looking at is figures that are congruent and then using that to get to area. So what we need to do is we're actually going to essentially, and I think of it as like sand. You have a bunch of sand up here in these smaller smaller two squares on the legs of the right triangle. You make a little hole here and all your sand starts pouring into this bigger one. And when all the sand dribbles out, it fills up this larger square at the bottom. Now what we're going to do is we're actually going to figure out where this dividing line is, where all of the area for one square, versus all of the area from the other square is going to go. So the key part of this whole proof is finding this dividing line right here. Okay, so what we're going to do is we're actually going to drop a line that is perpendicular to BC, perpendicular to your hypotenuse. So notice there's your dividing line, and it has to pass through your point A. So that's the trick of this whole proof. In other words, that guy. And the claim is, and this is what we'll prove, the claim is then that the area of BMLD, the little rectangle, is exactly the same as the area of ABFG, that little square. In other words, the stuff that's highlighted in red right now. Then what we'll show is, hey, the area of the other rectangle that's left is the same as the area of the other square that's left, now the one that's highlighted in blue. And notice this then allows us to use one of our common notions and add things together. We'll then get that the area of the entire square is, and there's actually going to be a middle step here, is going to be the area of BMLD plus the rectangle CMLE, and since we already know that those guys are equal to the area of the squares, that'll then give us the result that we care about, because remember, the sum of the areas of the squares on the legs equals the sum of the area of the square on the hypotenuse in formulas literally means we are trying to get to that result.